Jupiter has long been considered the ultimate giant, a planet so large that more than 1,300 Earths could fit inside it. But far beyond our solar system lies HATP 67a(b), one of the largest planets ever discovered, a world so immense that even Jupiter begins to feel small. Today, we'll journey beyond the limits of our solar system to discover a world so enormous that it forces us to rethink what the word planet even means. Get ready? Let's begin. Think about the largest planet in the universe. Your mind builds it automatically, without hesitation. It is enormous, a dark, suffocating mass, hanging in space like a bruise on the fabric of the cosmos. Storms the size of entire continents churn across its face in perpetual violence. Bands of churning gas, colliding and tearing apart in cycles that have run for longer than Earth has existed. The gravity is ferocious. Anything falling toward it accelerates past the point of return within seconds, crushed by a pull so overwhelming that the distinction between falling and being swallowed becomes meaningless. Moons orbit it like debris trapped around a drain, dozens of them, some large enough to qualify as worlds in their own right, all of them bound in permanent servitude to something so massive it reshaped the architecture of the entire system around it. The deeper you go into this imagined world, the hotter it gets, the denser it gets, the more violent it gets. There is no surface, just compression without end. You can feel the weight of it even in imagination. That picture is wrong, not off by a degree or two, not approximately right, wrong from the foundation, constructed on an assumption so thoroughly embedded in human cognition that questioning it feels less like scientific inquiry and more like questioning whether fire is hot. Here is where that assumption was born. For somewhere between 1 and 2 million years, human beings survived inside a single brutal equation. Larger equals more dangerous. A lion is more dangerous than a house cat. A taller wave kills more readily than a shorter one. A larger volcano erupts with more violence than a smaller one. Every single day, across every environment our ancestors ever occupied on this planet, this rule delivered without exception. Bigger meant more powerful. Bigger meant more threatening. Bigger meant more of everything that determined whether you lived until tomorrow. This is not a flawed rule. It is a spectacularly effective one. It worked so consistently, across so many generations, across so many different landscapes and predators and natural disasters, that the human nervous system stopped treating it as a conclusion reached through reasoning and started treating it as a reflex that fires before reasoning even begins. You do not calculate that the larger predator is more dangerous. You feel it instantly, in your chest, before your conscious mind has finished forming the thought. That feeling is the compressed inheritance of 1 million years of ancestors who were slower to feel it and therefore left fewer descendants. The problem is not the rule. The problem is the address. The rule was calibrated for Earth for pressures and temperatures and densities that fall within a very specific range, where volume and mass tend to travel together. On Earth, bigger things are almost always heavier things. A boulder outweighs a pebble. An ocean liner outweighs a rowboat. A mountain contains more rock than a hill. The correlation is so reliable across the scales of everyday human experience that the brain encodes it not as a pattern, but as a law, something that holds everywhere, at every scale, under every condition. Scientists carried that same intuition into the early decades of planetary astronomy. And for a long time, the solar system seemed to confirm it. The larger planets were also the more massive ones. The smallest planets were dense and rocky. The largest planet, Jupiter, was also the heaviest, the most gravitationally dominant, the one that had literally sculpted the orbital architecture of everything around it. The rule held in science just as it held in daily life. Nobody had compelling reason to challenge it. But a pattern is not a law, and the universe operates at conditions that make Earth's entire range of experience look like a single pixel in an image that spans continents. The distinction that unravels everything is this: radius and mass are not the same measurement. They are not even measuring the same property. Radius tells you how much space an object occupies. Mass tells you how much matter that space actually contains. On Earth, these two numbers move together because the substances filling that space are dense enough to make the relationship feel inevitable, but under conditions of extreme temperature, extreme radiation, and gravitational environments that nothing on this planet can replicate. These two numbers can be pulled so far apart that the relationship between them becomes unrecognizable. Consider this. Place a balloon the size of a house next to a marble of solid lead. The balloon occupies thousands of times more volume. The marble contains thousands of times more mass. Which one is larger? The answer depends entirely on what you are measuring. And in the universe, the distance between those two answers can grow to scales that no laboratory, no simulation, no terrestrial intuition can adequately prepare you for. A planet can be physically immense wider than anything your instincts default to imagining, while carrying a surprisingly modest amount of actual material. Not because something was stripped away, but because the material it contains has been heated, expanded, and inflated into a volume that its own gravity never could have produced under ordinary conditions. If size and power are two entirely different things, then what exactly is the largest planet telling us? And if the intuition you have carried your entire life about what big means is built on a foundation that only holds within a narrow band of earthly conditions, how many other things about the universe are you understanding wrong right now? Without any awareness that you are wrong at all. But before we get to the planet that breaks every rule, you need to understand what all of humanity has used as the standard of greatness for centuries, and why that very standard is the most perfect trap the universe has ever set. Every civilization that ever looked up at the night sky eventually landed on the same name, Jupiter, the largest planet in our solar system, and for most of recorded history, the largest object anyone had ever managed to put a number on? The numbers themselves are almost absurd. Jupiter's diameter measures 142,984 kilometers, roughly 11 times wider than Earth. Its volume could swallow 1,321 Earths and still have room left over. Its mass equals 318 Earths, which sounds impressive enough until you hear the comparison that actually matters. Jupiter is heavier than every other planet, moon, asteroid, and comet in the solar system combined, and then doubled. These are not statistics meant to impress you at a dinner party. They are the entire reason Jupiter earned its title, the king of the solar system. Jupiter's gravity has been carving the architecture of this solar system for 4.5 billion years, and it has never once stopped working. It shaped the asteroid belt into the thin scattered ring we see today, preventing loose rubble from ever clumping into another rocky world. It has flung billions of objects out of orbits that would otherwise have sent them spiraling toward the inner planets, acting like a cosmic doorman standing guard at the entrance to the neighborhood where Earth happens to live. Scientists have given this role a name, the Jupiter Shield Hypothesis. Simulations built by planetary researchers suggest that without a planet of Jupiter's mass sitting exactly where it sits, the rate of asteroid impacts striking Earth could be significantly higher than it has been across our planet's history. High enough, some of those models suggest, to have repeatedly interrupted the long-yas fragile climb of complex life before it ever produced anything capable of building a telescope. And Jupiter did not just protect a system. It built worlds of its own. Ganymede, one of its 4 largest moons, is physically larger than the entire planet Mercury, and it generates its own magnetic field, a feature no other moon in the solar system can claim. Europa hides a liquid water ocean beneath a shell of ice, an ocean that may hold more water than every ocean on Earth combined. And Io, yanked and squeezed without mercy by Jupiter's tidal pull, has become the most volcanically active body anywhere in the solar system. Its surface caught in a near-constant state of being melded and remade. This is the version of Jupiter most people carry in their heads and on paper. It earns every bit of its reputation. It is the heaviest. It exerts the strongest gravitational pull of any planet orbiting our sun. It commands 95 confirmed moons, more than any other planet. It hosts the largest storm ever measured in the solar system, the Great Red Spot, a hurricane that has been raging for centuries and is wide enough to swallow Earth whole with room to spare. Every single fact about Jupiter agrees with the same ancient rule your brain inherited 1,000,000 years ago. Bigger means more powerful. So when astronomers eventually pointed their instruments toward other stars and began hunting for planets beyond our own solar system, the question they asked was not really a question. It was an assumption wearing the disguise of curiosity. What does the Jupiter of other solar systems look like? Underneath that question sat a quiet expectation. Nobody bothered to state out loud, because nobody thought it needed stating. Whatever astronomers eventually found out, there would have to be bigger, heavier, stronger, a super Jupiter, scaled up to match whatever grander star it happened to orbit. For decades, nobody seriously doubted this. The logic felt airtight. The evidence, drawn entirely from the only solar system humanity had ever studied up close, was completely consistent. Jupiter stood at the top of the ladder, and it seemed obvious that the next rung up could only look like Jupiter. Just larger, just heavier, just more of everything that already made it the king it was. This is precisely the trap that science has a name for: confirmation bias, quietly built into the theoretical models themselves. It is more dangerous than an ordinary mistake because it never announces itself. It hides inside the very tool you're using to think, nodding along with every question you ask it, because the question itself was shaped by the bias in the first place. And then, in 1995, it happened, a discovery that did not just break that expectation, but forced the entire astronomical community to look back from the very beginning at a question they thought had already been answered. How do giant gas planets form? And where can they exist? Before 1995, humanity knew of 9 planets. Later that number would shrink to 8, once Pluto was reclassified and quietly demoted from the family portrait. But the real story was never the head count. It was the model sitting underneath it. A model so tidy, so internally consistent, that nobody felt any urgent need to question it. The model said this: small rocky worlds form close to their star, where heat burns away light gases and leaves only solid material behind. Giant gas planets form far from their star, out in the cold where ice and vapor can condense and pile onto a solid core large enough to eventually pull in enormous amounts of hydrogen and helium. This was not a flimsy guess stitched together from hope. It was a theory built from fundamental physics, and it had one perfect piece of supporting evidence sitting right in our own backyard. Our solar system followed the rule precisely. Rocky planets close in, gas giants far out, case closed, or so it seemed. Then 2 astronomers in France quietly broke it. Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory, were using a technique called radial velocity. The idea is simpler than it sounds. A star does not sit perfectly still while a planet orbits it. The planet's gravity tugs back, just slightly, and the star wobbles in response, like a much larger person being gently pulled off balance by a small dog straining at the end of its leash. You may never see the dog directly, but you can absolutely see the person stagger. What Mayer and Queloz detected was a wobble belonging to an object with roughly half the mass of Jupiter, orbiting a star called 51 Pegasi, completing one full orbit every 4.23 days. To put that in perspective, this meant the planet sat closer to its star than 0.05 astronomical units, a distance 8 times closer than Mercury sits to our own sun. Estimated surface temperature came in above 1,000 Kelvin. This was a world with no morning and no evening in any sense a human being would recognize. Just one face locked in permanent, merciless daylight. The scientific community's first reaction was not celebration. It was suspicion. Multiple independent research teams tried, in good faith, to tear the result apart and prove it was an instrument error or a misread signal. None of them succeeded. The planet was real. And it was sitting exactly where the established theory said nothing should ever be able to form. Mayer and Queloz would eventually receive the Nobel Prize in Physics in 2019, which is perhaps the highest compliment science can offer an idea, being doubted relentlessly for years and surviving every single attempt to kill it. Once the door opened, it did not close again. The list of these so-called hot Jupiters grew quickly, and every new entry asked a sharper question than the last. The first oddity was simple geography. Why are these planets here at all? The leading answer became disk migration, the idea that giant planets form far from their star exactly as predicted, then get gradually dragged inward by friction with the leftover gas and dust disk surrounding a young star, sliding closer over millions of years like a marble rolling slowly toward the drain of a tilted bowl. The second oddity was stranger and harder to explain away. The relationship between a planet's mass and its physical size stopped behaving the way it should. Some hot Jupiters were heavier than our own Jupiter, yet roughly the same size. Others were noticeably lighter, yet significantly larger, and a troubling handful were both lighter and bigger at the same time. A combination ordinary physics had no easy way to justify. By combining transit photometry, which measures how much starlight dims when a planet crosses in front of its star, with radial velocity, which measures mass, astronomers could finally calculate density. Some of those densities came back below 1 gram per cubic centimeter, lighter than ordinary water. A new term entered the vocabulary of planetary science: inflated hot Jupiters. Planets puffed up far beyond anything theoretical models had prepared anyone to expect. For the better part of a decade, one question sat at the center of the field, refusing to be ignored. What kind of energy keeps a planet inflated like this? Where does it come from? And how deep inside the planet does it actually reach? Because warming a planet's outer atmosphere is not nearly enough. To swell an entire world, that energy has to punch all the way down toward the core. The answer involves a physics mechanism you already know intimately from everyday life. You simply never imagined it operating at the scale of an entire giant planet. Scorched and swelling under heat, it cannot escape. Cold gas giants are not frozen statues hanging quietly in the dark. They are constantly shrinking. Jupiter itself was once 30 to 40% larger than it is today, back when it first formed. And it has been slowly contracting ever since, across 4.5 billion years of quiet, patient cooling. The mechanism behind this is almost embarrassingly simple. When a giant planet forms, it carries an enormous amount of gravitational energy left over from its own collapse, and that energy has nowhere to go but out, leaking away gradually in the form of heat. The planet cools, it contracts, it settles into a stable size. This is basic physics, the kind that behaves itself and shows up on time. For a cold gas giant sitting far from its star, if you know its mass and its age, you can calculate its radius to within a few % of the real answer, almost every time. So why does a planet like HATP 67b refuse to follow that script? The everyday mechanism hinted at earlier turns out to be something you have lived beside your entire life without ever thinking of it as cosmic. It is the same physics at work inside an electrical wire. The most common explanation for inflated hot Jupiters is called ohmic dissipation, and it begins with ultraviolet radiation from the star, which ionizes alkali metals like sodium and potassium sitting in the planet's upper atmosphere. Once ionized, that atmosphere stops behaving like an ordinary gas and starts behaving like a partial conductor. Ferocious atmospheric winds, driven by the staggering temperature difference between the scorched day side and the frozen night side, blow this newly conductive gas across the planet's own magnetic field, and that motion generates an electric current. Here is the part you already understand instinctively, even if you never connected it to a planet. That current travels downward into deeper layers of the atmosphere where resistance is higher, and resistance plus current always produces heat. The exact same principle that makes a toaster coil glow or an overloaded extension cord grow warm to the touch deep inside a hot Jupiter. That heat accumulates, slows the planet's natural contraction, and leaves it puffed up far beyond what its age and mass would otherwise predict. Researchers Daniel Thorngren and Jonathan Fortney mapped out exactly how efficient this heating becomes, finding that it grows stronger with more radiation, but then strangely weakens again at extremely high temperatures. Once the atmosphere becomes so conductive that it essentially short-circuits itself, ohmic heating is not the only mechanism at work. A second possibility is tidal heating, which begins with a slightly eccentric orbit. As a planet swings closer to and farther from its star across each lap, the gravitational pull on it changes constantly, stretching and squeezing the planet's interior over and over. And friction from that endless flexing generates heat. This is precisely the mechanism that turned Io, one of Jupiter's own moons, into the most volcanically violent body anywhere in the solar system. Its limitation is timing. Tidal forces tend to circularize an orbit fairly quickly, smoothing it into a perfect circle and shutting off this heat source in the process, which means it matters most in a planet's early life and fades dramatically after a billion years or so. A third mechanism, advective transport, needs no magnetic field and no eccentric orbit at all. It simply requires powerful atmospheric winds, predicted to reach several kilometers per second on the most extreme hot Jupiters, strong enough to drag superheated gas downward on the night side rather than simply spreading it sideways. This pushes the planet's internal temperature profile higher than flat, one-dimensional models ever anticipated, which means a warmer interior and a more inflated planet. Though confirming it requires far more complex three-dimensional modeling, the newest evidence, published in 2025, has reframed the entire conversation. Instead of heat needing to punch deep into a planet's core, researchers found that most hot Jupiter inflation comes from shallow heating, trapped near the boundary where radiation gives way to convection. Internal luminosity in these planets drops by 95 to 97% compared to models with no irradiation at all, which tells us something important. The star does not need to cook the core. It only needs to seal off the planet's escape route for heat at a shallow upper layer, and inflation takes care of the rest. Demographic studies of these worlds reveal something even stranger, a kind of sweet spot for catastrophe. Planets sitting between 0.37 and 1 Jupiter mass inflate the most violently of all because they carry too little mass for self-gravity to fight back effectively, while planets above that range have enough crushing weight to keep themselves in check. HATP 67b, weighing in at roughly 0.45 Jupiter mass, sits exactly at the burning center of that sensitive zone, and yet, even with every one of these mechanisms fully accounted for, nobody predicted what HAT net was about to find. A planet that did not just inflate, but swelled to a size that theoretical models flatly refused to confirm could even exist. Consider the contrast for a moment. The James Webb Space Telescope cost $10 billion to build. It carries a mirror 6.5 meters across, and it orbits the Sun at a distance of roughly 1.5 million kilometers from Earth, parked in a spot of space engineered with extraordinary precision. Yet HATP 67b, one of the most extreme planets ever confirmed, was first caught not by anything resembling that kind of machine, but by a telescope with an aperture of just 11 centimeters, roughly the width of a dinner plate sitting on your kitchen table. That is the instrument that helped unravel a planet extreme enough to challenge the physics of how giant worlds are supposed to behave. The discovery came through HATNet, the Hungarian Automated Telescope Network, which operates 2 stations, one at the Fred Lawrence Whipple Observatory on Mount Hopkins in Arizona, the other near the summit of Mauna Kea in Hawaii. Each of these modest telescopes watches hundreds of thousands of stars simultaneously, night after night, while automated software quietly searches for one specific signature, a small 1-inch periodic dimming that repeats with clockwork regularity. This is the essence of transit photometry. When a planet crosses in front of its star from our point of view, it blocks a tiny fraction of that star's light. The depth of that dip tells you the ratio between the planet's size and the star's size, and the rhythm of its repetition tells you the planet's orbital period. HatNet collected its earliest hints of this system between 2005 and 2008. A complete, fully captured transit followed on the 28th of May, 2012, observed with a 1.2-meter telescope at Whipple, with 5 additional partial transits recorded between 2011 and 2013. But a transit alone, no matter how clean, can only prove that something exists and reveal how large it physically appears. It cannot tell you how much that something actually weighs. And without mass, there is no way to calculate density. Without density, you cannot tell whether you are looking at a planet, a failed star known as a brown dwarf, or something stranger still wearing a planet's disguise. The standard tool for solving that problem is radial velocity, the same wobble detecting technique that uncovered 51 Pegasi b decades earlier. Precise enough in the best circumstances to register a stellar velocity shift smaller than 1 meter per second, slower than an unhurried person strolling down a sidewalk. But EHATP67 refused to cooperate. It is an F-type star spinning with a projected velocity of roughly 36 kilometers per second, 18 times faster than our own sun rotates. That speed smears and broadens every spectral line the star produces, burying the planet's faint gravitational signature underneath a wash of stellar noise. Observations at the Keck Observatory between 2009 and 2012 managed only to establish an upper limit, less than 0.59 Jupiter masses, nowhere near enough to confirm what the planet actually was. The breakthrough came from a different technique entirely, called Doppler tomography. Rather than measuring the star's overall velocity as a single number, this method tracks the planet's shadow as it slides across the face of a rapidly spinning star. Every region of that rotating surface moves at a slightly different velocity relative to an observer on Earth, producing its own distinct Doppler shift. As the planet blocks each region in sequence, it leaves behind a moving velocity signature traveling across the spectrum, a signature that cannot be faked by a background star or mimicked by instrumental noise. 2 independent Doppler tomographic detections ruled out every remaining false positive scenario. A related measurement, the Rossiter-McLaughlin effect, captured at the Galileo National Telescope, revealed something equally important. The planet's orbital tilt measured just 2.2 degrees, plus or minus 0.4 degrees, nearly perfectly aligned with its star's equator. That alignment carries real physical meaning. It points toward disk-driven migration, a planet sliding inward gradually through friction with the gaseous disk left over from its star's formation, rather than violent gravitational chaos, which tends to leave orbits tilted or even running backward. The confirmation paper, published in 2017 by George Zhou and colleagues in the Astronomical Journal, settled on a radius of roughly 2.085 Jupiter radii, paired with a mass somewhere between 0.056 and 0.59 Jupiter masses. An upper limit is not a mass. A planet weighing 0.06 Jupiter masses and a planet weighing 0.55 Jupiter masses are 2 fundamentally different objects, with different internal structures, different histories, and entirely different fates ahead of them. For 8 years, across multiple research teams and multiple observing campaigns, the star simply kept winning. Its own furious rotation continued hiding the answer. Then, in 2025, a new generation instrument, paired with a statistical method never applied quite this way, before produced a number that changed everything we understood about why this planet still exists at all. 8 years spent holding an imprecise number is 8 years spent unable to answer the most basic question anyone could ask about this planet. Should it even still exist? The theoretical answer had been clear from the start. A planet with a density below roughly 0.1 grams per cubic centimeter loses its atmosphere fast enough to be destroyed in under 100 million years. The HATP 67 system is more than 1 billion years old. If the planet's density really was as low as everyone feared, it should have vanished long before humans ever pointed a telescope at it. The instrument that finally cracked this open was the NEID spectrograph, a new generation tool mounted on the 3.5-meter WIYN telescope at Kitt Peak National Observatory in Arizona. Built for an extraordinary level of velocity precision, but precision alone was never going to be enough, because this star presented a problem with two heads. The first was familiar by now, that furious 36 kilometer per second rotation, smearing every spectral line into noise. The second was new and far more insidious. The star's own rotation period, 5.40 days, sat almost exactly on top of the planet's orbital period, 4.81 days. Those two numbers landed close enough to each other that the star's natural activity signal and the planet's gravitational signal began bleeding into one another, tangled so tightly that no simple subtraction could pull them apart. The solution came from a statistical method called a constrained quasi-periodic Gaussian process. In plain terms, researchers built a detailed noise map out of the star's own activity pattern and then subtracted that map from the combined data set, isolating what was left over as the planet's true signal. This approach pulled together ground-based photometry, data from the TESS mission, and the new NEID radial velocity measurements into a single unified analysis. The team behind it, led by Gavin Wang, published their results in 2025. For the first time, the number that came back was not a ceiling. It was an actual measurement. The planet's mass settled at 0.45 Jupiter masses, with an uncertainty of plus or minus 0.15. Its refined radius came in at 2.140 Jupiter radii, with an uncertainty of just 0.025. And from those two numbers together came something almost impossible to picture: a density of 0.061 grams per cubic centimeter. To make that number mean something, you need a comparison. Saturn, the least dense planet in our own solar system, comes in at 0.69 grams per cubic centimeter. Ordinary medical cotton wool sits somewhere between 0.1 and 0.15 grams per cubic centimeter. HAT-P-67b measures 0.061. It is lighter than cotton wool, lighter, in fact, than almost any solid or liquid material you could reach out and touch with your own hand. At the time this research was published, it ranked as the second least dense hot giant planet in the entire catalog of confirmed worlds. And this is where the real paradox begins. At a density of 0.061 grams per cubic centimeter, theory predicts a runaway escape process should already be underway. Atmosphere bleeds away into space. Gravity weakens as a result. Weaker gravity allows the atmosphere to bleed away even faster. And that feedback loop should have torn the planet apart in well under 100 million years. The HATP 67 system is estimated to be a more than 1 billion years old. By the theory's own logic, this planet should have disappeared roughly 900 million years ago. It did not. It is still here, still measurable, still sitting in front of our telescopes right now. So, why? The answer has nothing to do with the planet itself. It has everything to do with the star standing beside it. And that star is doing something no stable, well-behaved star is supposed to do. It is dying. To understand why HATP 67b has managed to survive this long, and why it is about to stop surviving entirely, you need to understand exactly what its host star is doing right now. And what it is doing is not shining steadily, it is dying. Most of the stars you have ever heard of belong to a category called the main sequence. Stars steadily burning hydrogen in their core in a stable, predictable way that can last for billions of years without much drama. Our own sun is the textbook example of exactly this kind of quiet, reliable behavior. HAT-P Astronomy-67 left that stage behind. It is now classified as a subgiant, a star that has begun running out of hydrogen fuel in its core and has started restructuring itself from the inside out, swelling in size and climbing in brightness as it moves along the long road toward eventually becoming a red giant. The numbers paint a clear picture of a star in transition, 1.73 times the mass of our Sun, 2.65 times its diameter, roughly 12 times its luminosity, and that same furious projected rotation speed of about 36 kilometers per second, 18 times faster than our own sun spins. The planet orbiting this star lives inside an environment most human language was never built to describe. HATP 67b circles its host at a distance of only 0.065 astronomical units, roughly 9.7 million kilometers. For comparison, Mercury orbits our Sun at about 57.9 million kilometers, which means this planet sits nearly 6 times closer to its star than Mercury sits to ours. Its orbital period lasts just 4.81 days. In the time it takes Earth to complete one single trip around the Sun, this planet completes 76. Its equilibrium temperature hovers around 1,900 Kelvin, a number that sits right at the boundary, separating what astronomers call a hot giant from what they call an ultra-hot giant. At this threshold, ordinary molecules in the atmosphere are torn apart into individual atoms and ions. The entire chemistry of the sky shifts away from the molecular world most of us picture and into a stripped-down atomic one. Given numbers this extreme, an obvious question follows. How has this fragile, puffed-up planet survived for more than 1 billion years without being torn apart? The answer lies in the star's own biography. For most of a star's main sequence lifetime, magnetic activity, which is the primary driver of extreme ultraviolet radiation, fades steadily with age. Young stars blaze with intense ultraviolet output. Older stars calm down considerably. For most of this system's long history, the extreme ultraviolet flux pouring off HATP 67 simply was not strong enough to trigger runaway atmospheric escape from the planet. Even given how astonishingly low its density already was, the planet existed in a kind of metastable holding pattern, inflated and fragile. Its atmosphere stretched thin, but never crossing into catastrophic, large-scale loss. That holding pattern is now ending. As a star transitions into the subgiant phase, its internal structure reorganizes itself. The core contracts, the outer layers swell, the effective temperature shifts, more importantly, total luminosity rises, and the composition of the star's radiation output changes along with it. That rising, extreme ultraviolet flux has now pushed past the exact threshold needed to trigger runaway escape from an impossibly low-density world like HATP 67b. Wang and colleagues, in their 2025 study, concluded that this runaway atmospheric escape is a genuinely recent development in the system's long history, not something that has been quietly happening for billions of years, but a process unfolding specifically now, in step with the star's ongoing evolution. We are watching this planet cross into what can only be described as a killing zone, while the star above it keeps growing brighter, with no sign of slowing down. That timeline carries a number attached to it now. Wang and colleagues estimate that HATP 67b will either be torn apart by tidal forces or swallowed outright by its swelling host star somewhere between 150 and 500 million years from today. 500 million years sounds like an eternity measured against a single human life, but the universe itself is nearly 14 billion years old, which makes 500 million years equal to roughly 3.5% of all cosmic time that has ever passed. On the scale the universe actually operates on, this is nothing more than the blink of an eye. And by sheer coincidence of timing, we happen to be watching during that exact blink. But simply describing a dying planet is not enough, because astronomers have not been left to speculate from a distance. They have actually watched its atmosphere pouring out into space. painting a tail across the sky that stretches for millions of kilometers. And what they found there turned out to be stranger than any theoretical model had prepared them to expect. Describing a planet as dying is one thing. Watching it happen is another. And watching it happen is exactly what several independent teams of astronomers have now done, using a technique called transmission spectroscopy. The idea works like this. As a planet crosses in front of its star, starlight passes directly through the thin shell of the planet's own atmosphere on its way to our telescopes. Atoms and molecules inside that atmosphere absorb very specific wavelengths of that light, leaving behind a kind of fingerprint buried in the spectrum. By comparing the spectrum captured during transit against the spectrum captured when the planet is safely out of the way, astronomers can identify exactly what that atmosphere is made of and what state it is in. One research team, led by Bello Arrufe and colleagues, used the Carmenes spectrograph at the Calar Alto Observatory in Spain to look closely at HATP67b. They found sodium, a fairly common signature already known from many other hot Jupiters, but they also found something rarer, ionized calcium. This detail matters more than it sounds. Ionized calcium typically only shows up in planets considerably hotter than HATP67b's measured equilibrium temperature would suggest. Its presence is a sign that the upper atmosphere of this planet is far more ionized than its temperature alone should allow. The same team also found absorption in the hydrogen alpha line and in the helium triplet near 1083 nanometers, both classic signatures of an atmosphere actively escaping into space. A second team, led by Gully Santiago and colleagues, pushed the investigation further using the Habitable Zone Planet Finder spectrograph at the Hobby Eberly Telescope in Texas. Over 39 nights of observation, totaling 13.8 hours of telescope time, they tracked the planet across its entire orbit. What they found was striking. Helium triplet absorption increased to as much as 10% during transit, an unusually strong signal. But the truly remarkable detail was timing. The helium signal began appearing before the planet itself had even started crossing in front of the star. That leading absorption extended outward from the planet by a distance equal to roughly 130 times the planet's own radius, which translates into millions of kilometers of helium gas streaming ahead of the planet along its orbit, like smoke trailing in front of a car instead of behind it. The explanation for this strange geometry comes down to a concept called the Roche lobe, the region of space surrounding a planet within which material remains gravitationally bound to the planet rather than to the star. The size of this region depends on the ratio between the planet's mass and the star's mass, combined with the orbital distance separating them. For HATP67b, an unusually low planetary mass, a heavier than average host star, and an extraordinarily tight orbit combine to shrink the Roche lobe down to a size that is tiny relative to the planet's own already inflated bulk. Once the planet's atmosphere physically expands beyond that boundary, the escaping material is no longer held by the planet's gravity at all. It begins falling toward the star instead. The reason that escaping gas forms a leading tail rather than a trailing one comes down to orbital mechanics combined with the Coriolis effect. Gas escaping from the day side, the side facing the star, gets caught up in the planet's forward orbital motion and curves ahead of it rather than dragging behind. A third team, led by Casasias Barris and colleagues, analyzed spectra averaged across multiple transits and confirmed the helium signal independently, estimating an effective radius at the helium wavelength of roughly 6 Jupiter radii. Compare that against the planet's actual physical radius of 2.14 Jupiter radii, and the picture becomes almost surreal, viewed in ordinary visible light. This is a planet just over twice the width of Jupiter. Viewed in the specific light emitted by escaping helium, it appears nearly 3 times larger than its own physical body. 3 independent teams, using 3 different instruments tuned to 3 different wavelengths, all converged on the exact same conclusion. This is a planet actively dissolving itself into the surrounding darkness. Based on one-dimensional Parker wind models, the estimated rate of atmospheric mass loss comes out to roughly 10 to the 13th grams per second, which translates into approximately 10 million tons of atmosphere disappearing into space every single second. 10 million tons every second. To understand what that number actually means, once you stretch it across longer timescales, and why it manages to be both catastrophic and somehow still not enough to kill this planet on its own, you need to place it inside the correct physical context. 10 million tons of atmosphere disappearing every second, spread across a single day. That comes out to roughly 864 trillion kilograms. Spread across a single year, the total dwarfs the combined mass of every piece of infrastructure human civilization has ever built. Repeated many times over. It sounds catastrophic. It is catastrophic, and yet the universe operates on its own sense of scale, one that can swallow numbers this large without even blinking. Consider the planet's total mass for context. HATP 67b weighs in at roughly 0.45 Jupiter mass, which works out to approximately 8.5 times 10 to the 29th grams. Set that against a current loss rate of about 10 to the 13th grams per second, and a simple calculation emerges. At today's rate, draining the planet's entire mass would take roughly 2.7 billion years. That number alone might tempt you to relax. The planet has time, except this is only the current rate, measured at this single moment in a much longer story, and it will only climb higher as the host star continues brightening and swelling. This is where the full shape of the problem comes into focus, because HATP 67b is not facing one death. It is facing two, arriving from opposite directions at the same time. The first death comes from above, as extreme ultraviolet radiation from the star intensifies. The rate of atmospheric loss increases with it, and that loss feeds directly into a positive feedback loop. Lose mass, and gravity weakens. Weaker gravity allows the atmosphere to escape even faster, which weakens gravity further still. A downward spiral with no natural brake built into it. The second death comes from below. The host star is currently swelling along its evolutionary path toward eventually becoming a red giant. Within the next 150 to 500 million years, the star's own surface will expand outward until it reaches or surpasses the planet's current orbital distance. Long before that final swallowing occurs, tidal forces from the star may already pull the planet beyond its own Roche limit relative to the star, ripping it apart into a thin, glowing disk of debris, rather than letting it survive intact long enough to be consumed whole. HATP 67b is not some isolated curiosity sitting outside the rest of planetary science. It stands as an extreme, almost theatrical example of a process that quietly shapes the entire population of known exoplanets. Astronomers refer to one piece of this pattern as the radius valley, a noticeable gap in the observed size distribution of exoplanets clustered around 1.5 to 2 Earth radii. Far fewer planets exist at that particular size than simple formation models would predict. And the most widely accepted explanation involves two related mechanisms: photoevaporation and core-powered mass loss. Smaller planets sitting too close to their stars get their atmospheres stripped away entirely by stellar radiation, shrinking down into bare rocky cores with nothing left to hold on to. HATP 67b is essentially the same story told at a vastly larger and more extreme scale. Every careful measurement of its atmospheric escape rate becomes another data point, feeding into the same photoevaporation models that astronomers apply to that entire smaller population of struggling worlds. So, here is where this leaves us. A planet under simultaneous assault from two directions, scorched from above by a brightening star, and threatened from below by that same star's slow, inevitable expansion. All unfolding within a window of time shorter than the entire age of complex life on Earth. But none of this should be mistaken for an ending. The matter streaming away from HATP 67b is not simply vanishing from the universe. It is being redistributed, carried off into a different shape, a different fate, somewhere else entirely. Before tracing where that escaping matter is actually headed, it helps to understand exactly what HATP 67b looks like, not from the distant clinical perspective of astronomy, but from the perspective of someone standing inside that very system, and that picture will permanently change how you imagine the word sky. The sky over HATP 67b is not blue. There is no sky at all in the ordinary sense of the word. No crisp boundary separating breathable atmosphere from the vacuum of space. What you would see instead is a gradient, a slow fade from something hazy and opaque into something almost entirely transparent, with no clean line marking where one ends and the other begins. The star itself would dominate that view in a way nothing on Earth can prepare you for. It occupies roughly 20 degrees of sky, about 40 times the angular size of our own sun as seen from Earth. This is not a modest disk politely sitting against a backdrop of stars. It is a wall of fire consuming a large portion of your entire field of vision. Conditions on the day side push past anything resembling familiar weather. Temperatures climb above 2000 Kelvin in the upper atmosphere, hot enough that ordinary molecules break apart into individual atoms. Sodium and potassium drift through the air as metallic vapor. Iron and magnesium can exist in gaseous form at these pressure levels. Elements you would normally think of as solid metal floating freely like smoke. The planet sits tidally locked, or nearly so, meaning the same face permanently points toward the star while the opposite side never receives direct light at all, leaving the night side hundreds to well over 1000 Kelvin cooler than the side facing the inferno. Along the terminator, the narrow boundary separating perpetual day from perpetual night, temperature swings violently across a distance shorter than the width of a single continent. Clouds may briefly condense and just as quickly dissolve within these thin bands. Equatorial jet stream winds, predicted to reach several kilometers per second, faster than the speed of sound here on Earth, carry heat from the scorched day side toward the frozen night side, though never quite fast enough to fully even things out. The internal structure of this planet bears almost no resemblance to Jupiter's. Jupiter's interior runs through clearly defined layers, a region of molecular gas giving way to liquid hydrogen, which transitions into metallic hydrogen under pressures exceeding 2 million atmospheres, eventually surrounding a dense core where pressure reaches roughly 40 million atmospheres and temperature climbs above 20,000 Kelvin. HATP 67b spreads the same amount of matter, actually somewhat less matter, across a volume more than 10 times larger. The pressure gradient running from its outer edge down toward its center is far gentler than Jupiter's. Any transition into metallic hydrogen likely occurs much deeper, if it occurs in any clearly defined way at all. There is no sharply layered structure here, only a soft, continuous fade from something close to vacuum down to something only slightly less close to vacuum. This is not a planet with a true interior in the way we usually picture one. It is a gradient stretched from emptiness towards something only marginally less empty. A concept called scale height helps put numbers to this strangeness. Scale height describes the vertical distance over which atmospheric pressure drops by a factor of roughly 2.718, and it rises with temperature while falling with gravitational pull on Earth. That scale height measures about 8.5 kilometers. On HATP 67b, it stretches to roughly 800 kilometers, nearly 100 times larger in absolute terms, and still about 4 times larger even after accounting for the planet's much bigger overall radius. The consequence works in 2 directions at once. This bloated atmosphere extends much farther into space, presenting a far larger absorbing surface for starlight, which makes it wonderfully easy to study through transmission spectroscopy. But that same stretched out structure also makes the atmosphere dramatically easier to lose to space entirely. Every layer of HATP HATP-67b, from its blazing dayside surface down to its hazy, undefined core, exists under pressure incompatible with any long-term future and just beyond the planet itself. Out in the surrounding darkness, something is taking shape that no planet anywhere in our own solar system has ever been capable of producing. That structure is the helium tail. And to understand fully why it exists, why it leads ahead of the planet rather than trailing behind it, and why it remains visible from a distance of 1,200 light-years, you need to understand the physics of a planet quietly turning itself into a comet. Picture the Roche lobe as a teardrop-shaped pocket of space wrapped around the planet, its narrowest point aimed directly at the star. That narrow tip is called the L1 Lagrange point, and it marks the precise boundary where the planet's gravity finally loses its grip. Once atmosphere pushes past L1, it stops belonging to the planet entirely. It crosses into territory governed by the star's gravity instead. This single detail explains why the escaping gas forms a leading tail rather than trailing obediently behind. Gas that escapes from the dayside, the side facing the star, exits through L1 carrying roughly the same orbital velocity as the planet itself, but it now sits at a slightly closer distance to the star. Kepler's orbital mechanics demand that anything closer to a star needs a higher velocity to maintain a stable orbit at that distance. The escaping gas, still moving at the planet's older, slower velocity, suddenly finds itself moving faster than it needs to for its new, tighter position. That excess speed carries it forward ahead of the planet, sweeping it into a leading tail. The Coriolis effect, a consequence of watching this unfold from within a rotating orbital frame, bends that trajectory even further, curving the escaping material into the shape astronomers actually observe. A trailing tail forms too, though a fainter one. Gas escaping through the opposite point, L2 on the far side of the planet, away from the star, carries velocity suited to a slightly larger orbit than the one it is actually on. That gas lags behind the planet's motion instead of racing ahead of it, producing a weaker, dimmer tail trailing in the planet's wake. None of this material simply drifts away passively. It is actively launched outward by a mechanism with a long pedigree in astrophysics called Parker wind. The planet's upper atmosphere, its thermosphere, gets superheated by extreme ultraviolet radiation to roughly 9,900 Kelvin, nearly 5 times the planet's overall equilibrium temperature. That ferocious heat creates an enormous pressure gradient, shoving gas upward and outward with such force that it accelerates straight through what is called the sonic point, the exact altitude where the outflow's speed matches the local speed of sound. Beyond that point, in the near vacuum of space, the gas keeps accelerating, crossing into supersonic motion. This is not a new or exotic kind of physics invented specifically for exoplanets. It is the very same mechanism responsible for the solar wind streaming off our own sun. The sun's corona is superheated by a process scientists still do not fully understand, and that overheated material expands outward, accelerating through its own sonic point until it becomes the supersonic solar wind that constantly washes over every planet in our solar system, including Earth. HATP-67b possesses what can only be accurately described as a planetary wind, governed by that exact same physics. The observational evidence for this tail structure is direct, not inferred secondhand. The helium signal begins appearing before the physical planet ever starts crossing in front of the star. Proof that the leading tail sweeps across the stellar disk first, arriving ahead of the planet itself. That same signal lingers after the physical planet has already finished its transit. Evidence of the fainter trailing tail following along behind. Even the variation observed from one transit to the next fits neatly into this picture, consistent with an ongoing interaction between the planet's own outflowing wind and the wind streaming off its star. A structure that is not perfectly static, but shifts and breathes across each orbital cycle. So which version of this planet is the real one? In ordinary visible light, HAT-P-67b appears as a tidy round disk measuring 2.14 Jupiter radii. In the specific light emitted by escaping helium, it becomes something else entirely, an asymmetric cloud stretched out ahead of and behind the planet, with an effective radius of roughly 6 Jupiter radii and a leading tail reaching millions of kilometers into space. What exactly is this planet? The honest answer depends entirely on which wavelength you choose to look through. That is not a poetic flourish or a clever metaphor. It is a literal physical fact. But the strangeness of HATP-67b is not confined to what it is losing into space. It runs deeper still, because the system surrounding it, its host star, and a distant binary companion lurking far beyond, conceals layers of history more tangled than any single planet could produce on its own. HATP-67 does not stand alone in space. Data from the Gaia mission confirms that this is a binary system, a red dwarf star carrying roughly 0.58 times the mass of our Sun and about 0.68 times its radius, orbits the host star at a projected distance of approximately 3,400 astronomical units. That works out to somewhere near 508 billion kilometers, a gulf so vast that this companion star exerts no meaningful direct influence on the planet's atmosphere or orbit today. Its influence, if any, would have to be historical rather than current, and one mechanism in particular offers a tempting explanation. In binary star systems, a distant companion can trigger long-term orbital oscillations in a closer orbiting planet through something called the Kozai leadoff mechanism, slowly cranking up that planet's orbital eccentricity over cycles lasting millions of years. A highly eccentric orbit periodically brings a planet swinging in much closer to its star, close enough to trigger tidal circularization, a process that gradually rounds the orbit out and effectively traps the planet into the tight, circular path it now occupies. It is a clean story, and it would explain a great deal. Except HAT-P-67b's measured alignment angle of 2.2 degrees argues directly against it. The Kozai leadoff mechanism typically leaves behind orbits that are noticeably tilted or even running backward relative to the star's equator, not orbits sitting almost perfectly flat against it. Disk-driven migration remains the favored explanation for how this planet ended up where it is. But the mere presence of a distant binary companion adds an unmistakable layer of complexity to the entire dynamical history of the system, a complication that cannot simply be waved away. A second oddity involves timing that feels almost too precise to be coincidence. The star's own rotation period measures roughly 5.40 days. The planet's orbital period measures 4.81 days. Those two numbers sit suspiciously close to one another. One possible explanation is tidal spin-up, a process where a planet locked into a sufficiently close orbit can transfer angular momentum to its host star through tidal interaction, gradually spinning the star up over time. Some researchers have proposed an alternative or complementary explanation, a magnetic interaction between star and planet that could link these two periods together directly, though that particular evidence remains actively debated within the field. What is not debated is this: a rotation speed of roughly 36 kilometers per second is unusually fast for a star at this particular stage of its evolution, unless some mechanism has been quietly pumping extra angular momentum into it over a very long stretch of time. Layer all of this together: a distant binary companion, a star spinning faster than its age alone would suggest, and a planet sitting in a suspiciously well-aligned orbit, and you get a system where nearly every individual detail leaves behind a readable trace of some earlier chapter in its history. This is the quiet, patient work of planetary archaeology, the practice of reading a system's present configuration closely enough to reconstruct the events of its distant past. HATP-67b as. Then, is not simply an extreme planet existing in isolation. It is the product of a tangled history unfolding inside an equally tangled system. And astronomers have only just begun learning how to read that history properly. But a planet's history is never only about where it came from. It is also about what that single planet's existence reveals about the broader population of worlds scattered across the galaxy, and about the single most unsettling question its very survival raises: how many planets like this one have already existed and already vanished completely? Long before humanity ever built a telescope capable of catching a glimpse of them, astronomers have a chart they return to again and again. A simple-looking plot called the mass radius diagram. One axis tracks how much a confirmed planet weighs. The other tracks how physically large it is. Plot every confirmed exoplanet with both numbers measured, and you get more than 5,700 individual points scattered across the page. Each one a real world. Each one a tiny dot of data representing years of patient observation by some team somewhere on Earth. Look at that chart as a whole, and most of those dots cluster into recognizable neighborhoods, groupings that theory can explain reasonably well. Rocky planets bunched together in one corner. Sub-Neptunes and mini-Neptunes occupy another. Gas giants spread across a third. The chart, for the most part, behaves the way a well-understood population should behave. Dense, where physics predicts it should be dense. Sparse, where physics predicts it should be sparse. But there is one corner of that chart that is almost entirely empty. And it is not empty by accident. That corner combines a radius greater than 2 Jupiter radii with a mass less than 0.5 Jupiter mass, planets large enough to dwarf Jupiter in physical size, yet light enough to weigh less than half of it. On paper, this should be a perfectly survivable combination. In practice, almost nothing lives there. The explanation is not that the universe struggles to build planets like this. The conditions required to produce something like HATP67b are not particularly rare. Inflated gas giants form regularly around stars across the galaxy, especially in that sensitive mass range where self-gravity is too weak to resist puffing up under stellar radiation. The reason that corner of the chart looks empty is something else entirely. Planets that wander into that region simply do not get to stay there for long. The theory behind this is precise enough to put a number on it. At a density below roughly 0.1 grams per cubic centimeter, runaway atmospheric escape switches on under sufficiently intense radiation, and once that feedback loop begins, a planet's theoretical lifespan in that extreme state drops to under 100 million years. Now run the probability of catching one of these worlds in the act. If a planet only spends 100 million years occupying this fragile, oversized, underweight configuration out of a galactic history stretching across roughly 10 billion years, then the odds of us happening to observe it during that narrow window come out to about 1% of its total possible lifetime. Turn that number around, and it carries an unsettling implication. For every single HATP67b that astronomers managed to catch sitting in that empty corner of the chart, right now, there could easily be dozens, possibly hundreds, that have already lived through this same fragile stage and quietly disappeared, long before any telescope on Earth existed to record them. This same pattern shows up at a smaller scale too, in a feature astronomers call the radius gap, a noticeable shortage of exoplanets clustered around 1.5 to 2 Earth radii. The most widely accepted explanation for that gap involves two related processes: photoevaporation and core-powered mass loss. Small planets sitting close to their star, carrying only a thin envelope of gas, get that envelope stripped away entirely by stellar radiation over time, shrinking down into bare rocky super-Earths with essentially no atmosphere left to speak of. HATP67b sits at the opposite extreme of that very same spectrum. It is not a small rocky world losing a thin wisp of gas. It is a giant, puffed-up planet losing an enormous, generously sized envelope. Different scale, same underlying mechanism, playing out at a size hundreds of times larger. It would be easy to dismiss the empty corner of the mass-radius diagram as simply a blind spot in our search methods, a region we have not gotten around to exploring properly yet. The data argues against that explanation directly. Survey missions like TESS and Kepler are specifically well-suited to finding exactly this kind of planet: large radius, short orbital period, frequent and easily measurable transits. These are, by a wide margin, some of the easiest planets in the entire galaxy to detect. If planets like HATP 67b existed in large numbers and simply sat there stably for billions of years, our surveys would have already found dozens more of them by now. The fact that we have not is not a gap in our search coverage. It is a gap in their survival. That absence becomes a kind of indirect evidence all on its own, evidence about the speed of destruction rather than the rarity of formation. Whatever exists in that corner of the chart gets removed from the population faster than new examples can form to replace it, which is precisely why the corner stays empty no matter how thoroughly astronomers search it. Every careful measurement collected about HATP 67b, its mass, its radius, its atmospheric escape rate, its likely remaining lifetime, becomes another concrete data point feeding into a much larger survival function, a statistical model attempting to describe how an entire galactic population of planets like this one lives and dies over cosmic time. So when you look at HATP 67b sitting there on the chart, alone in that nearly empty corner, you are not looking at an oddity that simply happened to form this way and will go on existing this way indefinitely. You are looking at one of a vanishingly small number of survivors caught mid-collapse, observed purely because the timing of human technology happened to align with the timing of its destruction. The scarcity of planets like this is not a story about how unusual their formation is. It is a story about how thorough their extinction tends to be. And every piece of this puzzle? The impossible size, the unbelievable density lighter than cotton, the helium tail stretching for millions of kilometers, the dying subgiant star brightening overhead, and now this nearly empty corner of the galaxy's planetary census. All of it converges on a single question. It is a question that has never once appeared explicitly in any peer-reviewed paper. Yet, it is the question every person following this story has almost certainly been quietly asking themselves the entire time. At what point does something stop being called a planet and start being called something else entirely? There comes a point in almost every field of human inquiry where a philosophical question quietly transforms into a physics question, and almost nothing in modern astronomy pushes harder on that transformation than the object we have spent this entire story examining. The International Astronomical Union settled on an official definition of the word planet back in 2006, and that definition rests on 3 separate criteria. The object must orbit a star, rather than orbiting another planet, or simply drifting alone through space. It must carry enough mass for its own gravity to pull it into a roughly spherical shape, a state scientists call hydrostatic equilibrium. And finally, it must have cleared its orbital neighborhood of competing debris, sweeping up or flinging away the smaller material that once shared its lane around the star. HATP 67e satisfies the first 2 of those criteria without the slightest controversy. It unmistakably orbits a star, and its mass is more than sufficient to round it into a sphere. The third criterion is where the entire definition quietly falls apart, because clearing a neighborhood was a rule written with our own solar system in mind, where planets sit far apart from each other and asteroid belts can be meaningfully tidied up over billions of years. Nobody on that committee in 2006 was thinking about a planet that might not even have a clean edge to begin with, an object actively dissolving into the surrounding vacuum, even while astronomers attempt to pin down its exact dimensions. This is the deeper problem hiding underneath the question of definitions. That 2006 committee was made up of brilliant people working with the best information available at the time, but they were essentially writing rules for a population of objects they had already met. The 8 familiar worlds of our own solar system, plus a handful of dwarf planets drifting at the edges. Nobody in that room was staring at the kind of evidence we now have sitting on our desks. A world whose very boundary refuses to hold still long enough to be measured once and agreed upon. Ask a seemingly simple question about HATP 67b. Where does the planet actually end? You will get 3 completely different answers, and every single one of them is grounded in solid, peer-reviewed measurement. The first answer comes from its optical radius, 2.14 Jupiter radii, the boundary defined by the altitude at which the planet's atmosphere becomes thick enough to block visible starlight during a transit. This is the number most casual summaries would quote, if you only had time for one. The second answer comes from its helium radius, roughly 6 Jupiter radii, an entirely different kind of boundary. This one chemical, rather than optical, marking the point out in space where the escaping helium gas remains dense enough to absorb specific wavelengths of starlight passing through it. And the third answer comes from its Roche lobe, a gravitational boundary that has nothing to do with light or chemistry at all, marking instead the precise line in space where matter stops being held by the planet's own gravity and starts being claimed by the star's gravity instead. 3 boundaries, 3 legitimate, scientifically defensible answers to a question that sounds like it should have one simple number attached to it. None of those 3 answers is incorrect. None of them is the single, final, complete truth either. They are simply 3 different lenses pointed at the same impossible object, each one revealing a different edge depending on what kind of physics you choose to measure. Step back and compare this honestly against Jupiter. Jupiter possesses a genuinely thin atmosphere, sitting on top of a deeply layered interior, with sharp, well-defined transitions as you travel downward, hydrogen shifting cleanly from gas to liquid, and then liquid to a metallic state. Once the pressure crosses roughly 2 million atmospheres, density climbs steeply and predictably the deeper you go. Jupiter has a real, physically meaningful inside, and a real, physically meaningful outside, the way a stone or a planet is supposed to. In the simplest sense, most of us grew up picturing HATP 67b offers nothing resembling that kind of architecture. What it offers instead is a long, slow, fading gradient, beginning somewhere slightly denser near its theoretical center, spreading outward through something close to vacuum at what we casually call its surface, and finally dissolving into genuine, unambiguous vacuum out, where its tail streams away into the dark. There is no sharp line anywhere along that progression, no clean seam where you could honestly say the planet stops and space begins. What astronomers are actually describing when they study this object is not a solid body with edges. It is an ongoing process, a continuous unfolding event, and we call it a planet largely because no better word currently exists in our vocabulary for something behaving quite like this. That raises an uncomfortable question about permanence itself, one that reaches well beyond the technical definitions astronomers argue about in journals. Every planet in our own solar system carries with it an unspoken promise of stability. At least across any span of time a single human life could ever directly witness, Earth has occupied its orbit for 4.5 billion years and shows no sign of leaving anytime soon. Jupiter will very likely outlast our own sun in some recognizable form, continuing to exist long after the sun has swollen, shed its outer layers, and quietly settled into a cooling white dwarf. HATP 67b carries no such promise whatsoever. Less than 500 million years remain before it is gone completely, either torn apart by tidal forces or swallowed outright as its own host star continues to swell. It has already survived for more than 1 billion years, a span of time almost impossible to hold in your head all at once. And yet, that entire remaining future amounts to less than 3.5% of however much time is left in the life of the universe. If the word planet is meant to imply something stable and something enduring, something built to last, does an object like HAT-P-67b genuinely earn that label, or should it instead be understood as something closer to a transitional state? Matter temporarily gathered into one particular shape for a while, before it inevitably comes apart and reorganizes itself into something else entirely. Somewhere else in the galaxy, the universe, taken as a whole, seems to take a strange kind of pleasure in constructing extremes of every conceivable variety, almost as though it is constantly testing the outer limits of its own rulebook, just to see where those limits actually sit. Neutron stars compress matter with such unimaginable violence that a single teaspoon scooped from one would weigh billions of tons if you somehow managed to bring it back to Earth. Supernovae release the entire stored energy output of an ordinary star within a matter of seconds, a detonation bright enough to briefly outshine an entire galaxy. HATP 67b sits at yet another extreme on this same spectrum of cosmic strangeness, an enormous volume of physical space wrapped around a startlingly small amount of actual matter. Every one of these extremes ends up teaching the same underlying lesson, whether the lesson arrives wrapped in crushing density or in barely there fluff. The categories we like to imagine are fixed, permanent, and absolute, usually turn out to be nothing more than convenient labels stretched loosely across a much longer continuous spectrum that we have only partially mapped so far. Perhaps the word planet was never describing a rigid, clearly bounded natural category to begin with. Perhaps it is simply marking one point along a smooth, unbroken continuum, beginning with a bare, rocky core, climbing upward through mini-Neptunes, ordinary Neptunes, Saturn, Jupiter, and eventually blurring into the realm of brown dwarfs. Those failed almost stars sitting at the very top of the planetary scale. HATP 67b reaches toward the strangest, most extreme far end of that entire continuum. And in doing so, it quietly turns to us and asks exactly where we think the label should finally stop applying. All of this carries the story back to the very idea it opened with. All the way back to a simple thought experiment about imagining the largest planet in the universe. Human beings instinctively link size with power, a rule etched into the nervous system across roughly 1 million years of survival on a single, modest, rocky world. HATP 67b proves about as clearly as the universe is ever likely to prove anything that this ancient rule simply does not hold everywhere. The largest object we have ever carefully measured may also be the single most fragile object we have ever carefully measured. Its enormous size never came from accumulating more material, the way a snowball grows by rolling through more snow. It came instead from being stretched relentlessly and continuously toward an absolute limit, and a limit, by its very definition, is precisely the place where things begin to break apart. HATP 67b is not the crowning achievement of planetary evolution, not some final polished example of everything a giant planet is capable of becoming. It stands instead as proof that the universe occasionally builds things that, by almost any reasonable expectation, should not be able to exist at all, and for the time being, lacking any better word in our entire scientific vocabulary, we simply continue calling them planets. And perhaps that is the most unsettling realization buried inside this entire story. Not that this fragile, swollen, bleeding world will eventually disappear, but that it is here, right now, at this exact moment, and we happen to build the right instruments, point them in the right direction, at exactly the right time, to catch sight of it before it was gone. We found HATP 67b using telescopes no larger than an ordinary dinner plate sitting on a kitchen table, pointed steadily, night after night, at a star located 1,200 light-years away from where you are sitting right now. Our own galaxy alone contains several hundred billion stars. The observable universe beyond it holds roughly 2 trillion separate galaxies, each one filled with its own staggering count of stars and planets. 5,700 confirmed planets sounds, at first glance, like an impressively large number. the product of decades of dedicated human effort and ingenuity. But remember what that number actually represents once you set it against figures that large. It is not a map of the universe. It is not even a rough sketch of one. It is a small handful of sand, lifted carefully from a single spot on a beach that stretches farther in every direction than the human mind can properly imagine, that leaves behind a question with no answer attached to it. And it is a question likely to remain unanswered for a very long time to come. How many planets like HATP 67b have already existed, swelled, bled away their atmospheres, and vanished completely, long before humanity ever managed to build a single instrument capable of catching even a brief glimpse of them? And how many more are out there right now, swelling and bleeding into the dark at this very moment, orbiting stars we have never once thought to point a telescope toward? Perhaps the night sky was never the still, frozen, motionless painting it appears to be from a quiet backyard here on Earth. Perhaps it has always been a film, running in extraordinarily slow motion, filled from edge to edge with objects being born, swelling outward, melting slowly away, and disappearing entirely. All of it unfolding across timescales too vast for any single human lifetime to register directly while it happens. And we, standing down here with telescopes barely larger than dinner plates and statistical techniques built to coax faint signals out of overwhelming noise, have only just begun learning how to read a handful of individual frames from that enormous, endlessly running film. The darkness out there is not something to fear. The darkness is an invitation.